has stayed 5 minutes after, I think, for many decades. But hey, Jacques.
Hello, how's it going?
Well, nice to see you. Or at least your smiling
Sort
countenance
of.
in your picture.
Sort of. Now you can see me.
Now I actually see you. There you go.
Right.
Nice to see you.
So sorry, I feel like I've interrupted something.
No, you haven't. We're just trying to decide how long to wait before officially starting.
You appeared at the 30 seconds before the hour, so there was just a discussion.
Weren't we waiting for
Right.
John?
So people are showing up in droves.
Yeah,
That's
there's
right.
one of my collaborators, Patrick, has just showed up.
All right. Well, Wadi, why don't you share and then I'll do the introduction.
Great. See if I can find the right thing to share. There we go.
Success.
Everybody can see that?
Yes.
Great.
Atmosphere. It's the Western Hemisphere colloquium. Welcome.
I'm sorry. That was one of my speakos. You know, I do everything by voice, and I.
Welcome to
You
the
can tell
Western.
I haven't proofread my slides very well. I said Western Hemisphere.
Yeah,
I don't know how I
yeah.
came up with it.
Well, this will be
Welcome to the
my
Western
first-
Hemisphere colloquium on geometry and physics. We're happy to have Wadi Taylor today from MIT, who will speak about middle intersection forms on singular elliptic Calabi-Yau fourfolds and applications to the standard model and to mirror symmetry. If you would like to ask a question, you are free to unmute yourself and just shout your question out, or you're free to put a question into chat, and I'll try to monitor the chat and relay important questions to Wadi. Wadi, go ahead.
Great. Thanks very much, Dave. Thanks for the invitation. And it's great to be here and see so many familiar faces in this Western Atmosphere colloquium. Yeah, somehow, as I say, my speaker, hopefully that's the worst of the speakos that we'll see. So what I'm going to talk about
we should rename the seminar series.
The whack up. So what I'm going to talk about today is some work, some recent work and some forthcoming work with a variety of collaborators, including in particular Patrick Jefferson, who's here, Andrew Turner, Manki Kim, Xingyun or Kobe Lee, and Paul Ullman. And this is really at the interface between the math and physics. I'm going to emphasize in this talk the more some of the more mathematical side of it, but basically the idea is to try to understand systematically the middle intersection on Calabi-Yau fourfolds in an organized way that enables us to more efficiently understand flux compactifications of F-theory, which can give us standard model constructions. And this has some neat applications to mirror symmetry, trying to understand the full intersection lattice of middle intersection of the Calabi-Yau fourfold with mirror symmetry. So I'm going to try to get to all those topics. Let me make sure I can actually, okay, there we go. So I'll start with talking about this general idea of understanding the middle cohomology and the resolution independence of the intersection structure, which is what we've been finding with Patrick and Andrew. I'll talk about standard model constructions. I may give that a little bit of short shrift because I want to make sure I have time to talk about the mirror symmetry application, which I think might be particularly of interest to this audience. So if I'm getting to about 20 minutes left and I'm still in the middle of section 2, I will probably move quickly to the end of that so I have a good block of time for the mirror symmetry. And again, please feel free to shout out if there are questions. So the first part of this is based on a recent paper that came out, as I mentioned, with Patrick Jefferson, who's here, and Andrew Turner, who's now a postdoc at UPenn. And the idea is to try to understand the middle cohomology on a fourfold, elliptic fourfold, and how this interplays with, for instance, chiral matter and 4D F-theory models. So let me just start. I suspect that a good fraction of the audience knows something about F-theory, but some may not. So let me just start with a brief overview of the ideas of F-theory and how this ties into elliptic Calabi-Yau fourfolds. So basically, F-theory is a non-perturbative description of type 2B string theory. One way to think about it is essentially as a dictionary that allows us to translate back and forth between elliptic Calabi-Yau manifolds, and physical theories, where we think of this as a compactification of type 2B string theory on some compact Kähler manifold, not a Calabi-Yau manifold, but some space like CP2 or CP3, which then acts as the base of an elliptic fibration. The axiodilaton of type 2B basically encodes the modulus of an elliptic fiber. And so we can think of an auxiliary 2 real dimensional, 1 complex dimensional elliptic curve over every point in the compactification space that gives us an elliptic Calabi-Yau. So if the base is a complex surface, we get a 6D theory. If the base is a complex threefold, we get a 4D theory after compactification. So the idea is that the singularities in the fibration encode the fundamental physics of the theory. And this was really the beautiful insight of Morrison and Vafa, was that you can go beyond perturbative type 2B and realize even exceptional gauge groups like E6, E7, E8 by configurations of singularities, which in the Kodaira in their own classification are associated with particular Dynkin diagrams associated with the geometry of the compactification. So basically, if you resolve like an A2 singularity, you get an A2 hat Dynkin diagram, which is associated with an SU3 gauge group. And in the physics, this actually encodes the gauge group of the underlying theory that you get after compactification. Similarly, at codimension 2, you have increased singularities, and through the Katz-Vafa approach, which Sheldon and Vafa developed, and more general, more recent analyses, we can understand how the matter representations can be understood in terms of extra singularities arising at codimension 2 loci, in particular at the intersection between these codimension 1 singularities. And in the type 2B language, these singularities are associated with so-called 7 branes, which are sources for the 2B axiodilaton. So for us, the playing field is a Weierstrass model encoding an elliptic fibration. So in general, such a Weierstrass model can be written in the form of a Weierstrass model for an elliptic curve, where the F and G coefficients become functions, or more carefully, sections of line bundles on the base. So that's the setup. We have a sort of a dictionary which tells us if we have a singular elliptic Calabi-Yau of dimension 3 or 4, we get a physics theory in dimension 6, real dimension 6 or 4. So there are 2 ways of thinking about F theory. One of them is as a limit of M theory, where you compactify on one further dimension and then take a series of dualities and limits. And much of the work on F theory has taken this point of view. From that point of view, it is necessary to explicitly resolve all the singularities to get a smooth manifold on which you can compactify M theory and then take a limit. Thus, if we have a singular Calabi-Yau, there might be multiple different resolutions which give detailed differences in the structure of the Calabi-Yau fourfold. In particular, the full set of quadruple intersection numbers, say, on a Calabi-Yau fourfold will be different after 2 different resolutions. But the philosophy of this talk is going to be to take the 2B description seriously, which basically means that we should, in principle, be able to read all the physics off from type 2B and then geometrically from the singular Calabi-Yau. And this is a viewpoint that Dave has advocated for and others have discussed over the years. I think Dave has a still upcoming paper. What is F theory?
Still upcoming, still upcoming.
Still upcoming, great. That takes this point of view. So what we want to do is identify resolution.
So Lottie, this means that it's intrinsically non-perturbative and we can't think in terms of supergravity?
That means that it's intrinsically non-perturbative. There are various things we can say in terms of supergravity, but for example, the exceptional gauge groups are intrinsically non-perturbative. The axiodilaton becomes strongly coupled somewhere in the compactification, except in special cases with a Sen limit. So most F theory compactifications are intrinsically non-perturbative because the axiodilaton varies over the entire tau moduli space over the course of the base.
Do you think Ramon charges are going to be classified by K theory?
Is that Greg?
Who else would ask a question like that?
Yes, I recognize you. I didn't see that. That's a great question. Which set of charges do you want to classify by K-theory?
The charges of the Ramon that source the Ramon fields. And while we're at it, Ramon fields themselves, but I'm not even sure we should talk about them if we can't talk about supergravity.
Right.
So
If you don't
Greg,
have
let
a
me
constant axial dilaton,
Greg,
if
let me make
the
one remark.
Ramon scalar is turned on, why should you have such a classification?
So Greg, there are PQ branes or PQ two-form fields, either way you want to look at it in these theories, and those are acted upon by SL2Z and therefore not distinguishable, right? SL2Z has to be gauged in this quantum gravity.
That's where I'm coming from. Yep.
And so I would say no, that the K theory can't really do it, because the 3 brane is not changed by SL2Z, but the 1 branes and the 1 branes and 7 branes are 5 branes I need to think about. But anyway, yeah.
Yeah, I think
Five
that's.
branes are
I think what Dave said is accurate. Because we have the SL2Z monodromies around the various branes, it's not clear that there should be a K-theory story. But so, Greg, I would say that the remarkable thing about F theory is that somehow the power of holomorphy gives us a global picture of the moduli space of solutions and a powerful way of describing both the gauge group and aspects of the matter content somehow in terms of algebraic geometry and topology without necessarily having a sufficiently complete tool set that we can compute in gory detail what would come out of the constants in the theory that you would need to do
Right. But
calculation.
you were just stressing that you didn't have, you're not going to be thinking about smooth resolutions in terms of, some limit of M theory on a smooth manifold. This is where my question's coming from.
Good.
Because
so
in the latter case, I would have thought that you could at least continuously connect to some weakly coupled supergravity description.
No, actually, in many cases, there's no, any case without a Sen limit, there will not be a continuous deformation of the moduli that takes you. Anything with, for example, an exceptional gauge group, there's no limit where you get a Sen limit or a weakly coupled description.
So should we should be thinking of this as some kind of place in the landscape where there's no connection to weakly coupled smooth manifolds, weakly coupled string theory on large smooth manifolds?
Yes, I think most F theory backgrounds fit in that category, but we can still say interesting things about them. And just to give you a little preview of where I'm going with this, I don't know how to actually do homology, intersection homology calculations on a singular variety. So what we will do is identify structure that is invariant under choice of resolution, and then hypothesize that that is the resolution independent structure, which hopefully some mathematicians who understand this intersection theory on singular manifolds better than we do can actually develop an axiomatic framework to prove. Does that make sense?
Yes, thank you very much.
Sure, good. So as I just said, what we want to do is identify structure which is resolution independent. The physics has to be independent of the resolution because the resolved manifold really only makes sense when you go to M theory, compactify an extra dimension, and go off on a Coulomb branch. In the physics of F theory, we should not have a resolution, so we should have some non-perturbative description. And there's some related work, some stuff that Sheldon and I have been doing recently as a generalization of Douglas Park Schnell to get at some of the fields from a direct 2B point of view, and some work that Grassi, Halverson, Long, Jameson, and Sung have done recently using string junctions to try to understand singular elliptic Calabi-Yau. So basically, the idea is we want to find a formalism for describing some aspects of the resolution-independent structure. So let's just talk briefly about the topology of elliptic Calabi-Yau fourfolds. Divisors on these guys are codimension 1 algebraic threefolds. In the F theory 2B language, these are associated with 7 brane loci. There's this nice formula by Chioda Tate Wazir, which says that H11 of the total space is H11 of the base plus the rank of the gauge group plus 1. And so we can think about that as counting the set of divisors, and we're going to use that to index the divisors. D0 will be our 0 section. D alpha will be pullbacks of divisors on the base. Di are Cartan generators for the various parts of the non-abelian gauge group. DA are going to be U1s, although we won't really deal with U1s associated with Mordell-Weil, and collectively we'll denote them by a capital I index. And non-abelian gauge factors will be supported on some divisor in the base, which is a linear combination of the base pullback divisors. Okay, so the elliptic, I'm going to focus on fourfolds. The fourfold has various Hodge numbers. H11 is the set of divisors. H31 is the set of complex structure moduli. In general, H21 is 0 or small, and we won't really deal with that. And we can compute H22 and the Euler character in terms of the other Hodge numbers. So the primary focus of the discussion today is going to be the vertical part of H4 cohomology, which is basically the span of the intersection of the divisors. So we denote a bunch of surfaces, Sij, as the intersection of di with dj. In general, that will be a redundant set of surfaces because there will be homology relations between those. Those span an integer space, which we'll call H22 vert. And you could define a couple different definitions for H22 vert, but for the purposes of this talk, we will take it as the integer span. So it's an integer lattice generated by the intersections of the various divisors. And this is of particular interest on the physics side, because if we impose fluxes, in the language of M theory, these would be G4 fluxes, and there's various other ways of describing that in type 2b. If we impose fluxes through those vertical cycles, we get chiral matter. So there's an orthogonal decomposition of the full H4 of the fourfold into the vertical part, which is this part just described here, spanned over C, the horizontal part, which comes from deformations of the complex structure moduli, and then a remainder part, as was pointed out by these folks, which is neither in the vertical nor the horizontal part. In some cases, we'll dig more deeply into a case later today, which does not have a remainder part, but a number of interesting fourfolds do have a remainder part. And this middle cohomology over Z has a unimodular intersection pairing, and that will be part of the focus of today's talk, is that unimodular intersection pairing on the entire H4, of which we have some computational tools that access the H22 vert part. So any quick questions about that structure? Because that's really this is the math structure that will be the central focal point of the talk.
Could you say something about why you call it vertical?
Huh. I'm not sure whether the vertical or the horizontal was in place first. Dave, do you know? You might have coined even part of this terminology.
There's a Hodge diamond, right? And the Hodge diamond, I would say, has H00 at the top and HNN at the bottom. And so you would have vertical going up with HPPs and horizontal going across. But if you want to orient your Hodge diamond a different way, you might have a different horizontal vertical designation.
But this is a part of H22, which is entirely vertical by what you just said.
No. It's not entirely vertical. It's only the part that's spanned by intersections of divisors.
Right. Part of H22 is horizontal, and part of it is in rem. Yeah, I other than what Dave said, I have no useful insight into how that term came into being.
I mean, in terms of the elliptic fibration, I don't say anything particularly vertical about that.
No,
this has nothing to do with elliptic vibration. This is defined in the absence of an elliptic vibration. Sorry, Dave.
It's a Hodge diamond. That's the only vertical horizontal part. It's the Hodge diamond.
Well, but I think, as Ron said, I mean, H22 sits in the middle of the Hodge diamond, right?
It does, but I'm not assigning H22 to be either vertical or horizontal, right? I'm assigning it to be, so the vertical part is the part that comes from intersections of divisors. The horizontal part is the part that comes from applying a one parameter.
Good. Yeah.
Deformation
So good. I think what you're saying, Dave, is that it's horizontal because it comes from a deformation of the part that came to the left, the H31.
That's right.
Yeah. Good. Okay. I hope that is satisfying, Ron.
Sure.
So let me briefly say something about where chiral matter comes in. So it was pointed out by Witten that the flux lives in H4xz with a possible half integer shift by the half of the second Chern class. And the flux satisfies various conditions. It's got to be 2,2 for supersymmetry. There's a bound on it, which is a tadpole bound on the total number of D3 branes. So the Euler character of the fourfold minus integral of G wedge G has to be a non-negative integer. Poincare, so then we have this flux, this fourfold flux, and we can integrate that four-form flux over various surfaces. And Poincare invariance tells us that if we want to preserve Poincare invariance in the low energy theory, the flux integrated over these surfaces S0 alpha, that is the intersection of D0 with D alpha, will vanish. So this is the integral of G over certain vertical surfaces in H22 vert. And if we want to preserve gauge symmetry, we have to integrate it to 0 over SI alpha, although for one of the constructions I'll talk about, we will make that non-zero to do a flux breaking of E7 to get some interesting standard model constructions. So the chiral matter is determined by fluxes through other vertical cycles, which are not of the form just mentioned. This is something that's been studied extensively in the F-theory and F-theory phenomenology literature. Donaghy and Weinholz, all these other folks, Beasley, Heckman, Waffa also have discussed this general idea, and there's an ever refined notion of what the surfaces are that we need to integrate over. But the basic idea is there are certain vertical surfaces that when we get a non-zero flux over those, we get chiral matter.
So why the
Yeah.
G is the four-form flux of M theory?
Yes.
So we are using the supergravity here.
We are using that, and what I'm going to do is use the four-form flux in supergravity and show that a part of the story is resolution independent and therefore must make sense even without desingularizing. So the only way I know to get at this is to start with G flux on a smooth manifold, but we will find that a piece of the structure doesn't depend on the resolution. So we're not doing a calculation in the singular manifold. We are doing a calculation in various resolutions and then showing we always get the same answer. And then hypothesizing that is a resolution independent mathematical object that should be defined without resolution.
Okay. There are, by the way, there are torsion refinements of the tadpole constraint. I don't know if
I believe that.
I don't know if has that been studied at all? I mean, I know how to formulate it. I don't know if it's been studied in this F-theory context.
I don't know the answer to that.
I don't think it has.
So I'm not sure. Yeah, I'm not sure if the torsion would contribute to the D3 brane tadpole, because that's an integer.
I'm talking about the end, that what you wrote is the tadpole condition. That has a torsion refinement, depending on how you model the C field of M theory.
Right. You mean that somehow instead of taking values in Z, it's taking values in Z cross twisted product some torsion group or something?
Yeah, I mean, there's an equation that takes place in H8 with Z coefficients, which could have torsion.
That's interesting. I didn't really appreciate that, and I'm not sure what the physics of that would be, but that might be interesting to understand better. Good. Thanks, Greg. Okay, so let's talk about this intersection form, and this is sort of the key to what I'm going to say today. Again, in order to actually calculate things, in general, people have taken specific resolutions and then calculated in that way. So what we're going to do is to identify a resolution independent structure, which allows us, once we know what the answer is, to do a systematic and base independent analysis for a lot of gauge groups. So the basic idea is the following. We can write down the quadruple intersection numbers on a Calabi-Yau fourfold, and in general, they will depend on the resolution. So we have some MIJKL. One way to think about that is to organize it as a matrix. So we can use pairs of indices and write down a matrix where the indices in the matrix are pairs of indices, ij and kl. So mij kl is just defined to be the intersection of sij with skl, which is just some of the quadruple intersection numbers. We can then write the flux equation. So theta ij, the flux of G through Sij, is then just this matrix multiplying some vector. So we can write everything in terms of linear algebra. And here the G is just the Poincare dual of the surfaces multiplied by some coefficients. So the phi KLs are parameterizing our flux. So if we take that matrix M and we remove the null space, which is associated with trivial elements in homology, remember I mentioned that there's a redundancy in the set of Sijs, we get some matrix which I'll call M red, which is non-degenerate. And the observation is that in a broad class of cases that we've studied, the resulting M red is actually resolution independent up to an integer choice of basis. And we've seen this in a huge class of examples. We have a general argument that this must be the case, although it involves an assumption about essentially which coset a piece of the matrix lives in relative to the inverse Cartan of the gauge group. And I'll give you a picture of that in a minute. But basically, this seems to be true. We can't prove it rigorously, but it seems that this reduced intersection form, after we get rid of trivial homology elements, is independent of resolution, and therefore should be thought of as the intersection form on the singular elliptic Calabi-Yau without worrying about having to do a resolution. Furthermore, we can write down explicit formulae for this. We can compute the general form of this for various gauge groups over general basis using a systematic approach to doing the resolution that builds on some earlier work of Mboiwa Sole and Patrick Jefferson and Monica Kang, which, building on that a bit further, we can resolve these general gauge groups over general basis, and we get a very clear structure. So for example, if we have a simple non-abelian gauge group, we can choose a basis, we can get rid of the other surfaces using homology relations, choose an independent set of S0 alpha and S alpha beta, where the size of each of those is equal to H11 of the base, and those are equal by Poincare duality on the base. The set of Si alphas and some possible set of matter surfaces Sij, and we get a matrix that looks like this. So this is always the form for M red, where the asterisks depend on resolutions, but for every pair of resolutions, there is an integral linear transformation that matches those two things. And there's always a non-integer change of basis that puts it in the form here, where basically this can be thought of as a matrix acting on a sublattice of z to the k. And this matrix in the bottom right, M phys, is all you need to encode the physics of chiral matter and fluxes. So basically the story is that this is the form of the intersection matrix on H22 vert for a completely general theory. It's a little more complicated if we have U1 factors, but if we have just non-abelian factors, this middle block here, we have the inverse Cartan matrix. Sigma is the divisor supporting a given gauge factor, and then these are intersections of divisors. Okay, so this is kind of the central idea on which most of the talk is going to build. So the idea is that there's a resolution independent form for this intersection form, and we can use it to compute everything we want. Any questions about that?
Remind us what's the difference between the alpha and the alpha betas and the IJs?
Sure. The alphas are indices on the base. So these are pullbacks of base divisors. The I's are in the Cartan. So basically everything in the upper left 2x2 block here this is all written in terms of intersection theory on the base. I should mention that the idea of these resolution structures from Azole, Jefferson, and Kang, and that we've got more general applications of uses of that, is to push forward the intersection structure in the fourfold to the base. So this is all written in terms of the intersection theory on the base. So you'll see that the upper left 2x2 block only involves divisors on the base, and K is the canonical class of the base. Whereas the 3-3 element block here, this kappa is the inverse Cartan of the inverse killing form. It's really the Cartan for ADE. Cartan matrix of the of the gauge algebra of the gauge group, and then sigma, these guys are all divisors in the base. So just to give you a quick idea, if we have, for instance, SU5 and we have chiral matter, we can write down this formula. We get, the thetas are the matrix M times some phi's. We get a formula that looks like this over a general base. And we can write down a formula for the multiplicity of the 5 plets on a general base in terms of the geometry of the base. Gives us a base independent formula for chiral multiplicities based on this resolution independent matrix structure. And we can do this for general gauge groups. There are some interesting questions regarding quantization that I'll come back to. Those require understanding the exact integer structure of the homology lattice. And again, what we're using here is the integer span of the SIJs. And it may be that there are rational combinations of the SIJs that actually lie in H4 of XZ. And what I've said so far is not sufficient to determine that, but they are relevant when we're trying to actually calculate the complete set of allowed multiplicities for some F-theory compactification. Okay, so that's sort of the first part. Any questions on the first part? I'm going to quickly go through some standard model constructions so I have time for the mirror symmetry, which, again, I think people here might find of most interest. Okay, so the standard model constructions are a couple of different constructions that basically use this technology. So first, I'll talk briefly about tuned standard model structures. This is based on a paper with Andrew Turner, another paper with Nikhil Raghuram and Andrew Turner, and then another upcoming paper with Andrew and Patrick. Couple of concepts that will be useful. There's a sense in which certain matter representations are generic in F-theory for a fixed group. And basically, these are the representations that appear in the largest dimensional branch of the geometric moduli space. For example, for SUN, the fundamental, the antisymmetric, and the adjoint are the generic matter fields. You have to fine tune the theory a lot to get more complicated things. There's various things you can say about that, like in this paper with Dave and Dennis Clevers and Nikhil Raghuram, we looked at exotic matter, which involves a lot more fine tuning. One relevant point here is that for the standard model, if we just take the gauge group SU3 cross SU2 cross U1, the matter we see in the standard model is very far from generic and involves a lot of fine tuning. So it's natural to go to the gauge group SU3 cross SU2 cross U1 mod Z6, which gives pretty much the standard model matter plus a few exotics. So in this work, especially the most recent upcoming work with Patrick and Andrew, we've constructed a universal G model, meaning so a universal G model is a class of Weierstrass models that realizes the full dimensionality of the moduli space of models with particular gauge groups. So for instance, the Tate models for the ADE, the Morrison-Park model for a U1 are universal models for those gauge groups. And so we have a universal model for this GSM, which has the Z6 quotient. It's kind of a messy looking Weierstrass model, which we got from unhiggsing a clever model that Nikhil Raghuram found for U1s with charges up to 4. It turns out that unhiggses to the most general model, which you can tune this standard model gauge group in. And a special case of this is these so-called F11 models that have been studied a lot that came out of the work of this group that recently quadrillion standard model solutions were found in that class. For this class of models, the generic matter includes the standard model matter plus 2 families of exotics. And so we can write down the most general model, and using this resolution independent intersection form, we can, in a base independent way, write down what kinds of fluxes, what kinds of multiplicities we can get. And in general, we get all 3 families of these things. And so we can generate huge families of standard model constructions. You have to tune 2 of the discrete parameters to get just standard model and no chiral matter, no exotic matter. So that's one construction. Any questions about that? Okay, a second construction.
May I ask a question, please? Just a notational
Please, yes,
question.
go ahead.
So for the universal Weierstrass model, the functions f and g had a lot of these things. What are they? These S's and D's?
These are parameters which are generic sections of certain line bundles. So this is a typical feature of these universal models. For example, a Tate model is one where you write the more general Weierstrass form, like y squared plus a1 xy plus you write it in terms of A1, A2, A3, A4, and A6. Those are generic sections of minus nk. These are similarly sections of various line bundles over the base. So it's just somewhat arbitrary notation for a whole bunch of choices of line bundles.
I see. So it's basically written in the date form.
In what?
So the model is essentially written in the date form.
Well, this is actually not even the Tate form. This is a more general. I mean, in the Tate form, we would see some A1 through A6s appearing in this.
Right. Yes.
Here we have a more exotic set of parameters that it's a more specific model that realizes this very particular. Like in the Tate form, you can realize an E8 by tuning the A's to vanish to certain orders. This is another class of models where we have a bunch of parameters, and this is the general structure, like the Morrison-Park model for U1s. Similarly, you write it in terms of a bunch of parameterized sections of line bundles.
All right, thank you.
Sure. Okay, so there's another construction which I just want to talk about briefly because I'm kind of excited about it. This is some recent work with Kobe Lee based on a short paper that came out recently and a longer one that will come out soon. Here are the ideas we're going to break in E7. So let me say a few general things which are helpful in understanding the landscape of Calabi-Yaus that will explain why I'm excited about this class of models. A comment is that we have at this point pretty strong evidence that most known Calabi-Yau threefolds and fourfolds are elliptic in the sense that there is a phase in which they have an elliptic fibration, that is a flop phase. If we look at, for instance, the Kreutzer-Skarka database of 400 million toric varieties where a hypersurface gives a Calabi-Yau, all but 30,000 of those manifestly have a phase where they emit an elliptic fibration. The other 30,000, many of them also probably do, but it's not as obvious. Okay, so most Calabi-Yaus seem to be elliptic, and there's also analytic arguments why that should be the case. Furthermore, as we found with Dave, most Calabi-Yaus, or most bases that support Calabi-Yaus, force certain Kodaira singularities because there are certain divisors that have very negative normal bundles. In the physics language, the negative normal bundle means that 7 branes are forced to nucleate on rigid loci, which give us gauge groups. So these include gauge groups like SU2, SU3, SO7, F4, the exceptional groups, but not SU5. So to get a standard model, it's natural to look at these rigid gauge factors, which are forced on you for a huge fraction of Calabi-Yaus, and try to get the standard model out of a subgroup of those. So typically, if you choose a base out of the set of possible bases, you will find there's a bunch of these so-called non-Higgsable or rigid clusters, which contain various products of gauge groups that only interact through gravity or scalars and hence are natural dark matter candidates. For example, for threefolds, if we look at the bases, the only bases that do not admit non-Higgsable clusters are the generalized Del Pezzos. And there's like a small number of those out of the toric bases. All but the orange ones admit lots of factors of E8 and F4, et cetera. Similarly for fourfolds, out of the 10 to the 3,000 approximate bases, maybe 4,000 of them lack these rigid gauge groups. So there are various ways of getting the standard model. I'm going to kind of rush to the end of this story because I do want to have time for mirror symmetry, but basically we can either tune or not tune. We can have a gut or not have a gut. And what I want to focus on here is taking one of those E7s, which is rigid, which is forced on you in a huge fraction, maybe 20, 30% of known threefold bases seem to have an E7 factor, and we want to break it. So we have this nice formula. The flux is the matrix times the phi's. And when we turn on fluxes in the I alpha direction, we'll break the associated Cartan directions. So we can break down to SU3 cross SU2. And you can do that in a unique way up to E7 automorphism for at least for root embeddings of SU2 cross SU3. And then you can turn on fluxes and preserve different U1 factors. Most of those end up having exotics. And it turns out that if you tune a flux so that you don't have exotics, you naturally get an enhancement to SU5. So there's a little bit of a complicated story where we have to proceed in 2 steps. We use vertical flux to break down to SU5, and then we have to turn on some remainder flux, which means we need to have a non-toric base. And this follows very closely the story of Beasley, Heckman, Vafa, and Donagi, Weinholt, and the many hundreds of papers on that, on constructing standard model-like things. But here, instead of starting with a tuned SU5, we're taking E7, breaking it with fluxes, and getting a standard model-like construction. And I won't go through this in detail, but if we just take the SU5 part of that, we can take a very simple example where we have the base, which is like a P1 bundle over a Hirzebruch with a particular normal bundle. We can turn on the fluxes, solve the flux constraints in the Kähler cone, and we find that the chiral multiplicity of the matter is 7 times one integer plus 4 times another integer. Because of the number of fluxes and the tadpole constraint, for a typical flux, those integers are either 0 or 1, and they have to have opposite sign. So the only non-trivial solution to that is +1 and -1, which gives us 3 generations. So it's very natural in that class of models to get 3 generations. Okay, that was super quick. I'm happy at the end to discuss that more, or now if there's other questions. Again, this is a nice construction. I'm excited about it because it's much more natural from the F-theory top-down point of view. If we look at all the elliptic Calabi-Yau fourfolds, a huge fraction of them have these rigid E6s, E7s, and E8s. And so this is a way of getting the standard model out of those rigid E7 factors. It would be nice to get them from E8, and there's a paper by Tian and Wang that talks about that, but it's much more tricky actually to get them from E8. And we can also get them from E6 using a similar construction. Pause briefly for questions on that, and then I want to save the last 20 minutes for mirror symmetry. Okay, I was getting very speedy there, but I'm going to take a breath and go slightly more slowly to try to really explain the mirror symmetry story, because I think it's very nice and people might appreciate it or have comments. So this is basically a story that has developed from some work with Yu-Qian Huang, my former student, Paul Ullman, and I are writing a paper on a general aspect of this. And then the particular thing I'll focus on today is some work with Patrick and Manki Kim in another paper to come out shortly. So the underlying observation here is that mirror symmetry basically factorizes for many toric hypersurfaces. And what I mean by that is that in the Badarev construction, the Calabi-Yau is associated with a hypersurface in a toric variety associated with a reflexive polytope. So it's basically encoded in combinatorial data, some polytope in k dimensions. And the mirror polytope, the polar polytope, gives us the mirror Calabi-Yau. One of these toric hypersurface Calabi-Yaus is elliptic if we can find a 2-dimensional reflexive polytope that is a subpolytope of our 3 or 4-dimensional or 4 or 5-dimensional polytope nabla. If we have such an elliptic structure where we have a nabla 2 which lives in nabla, and if in the mirror, in the dual polytope, the mirror 2 polytope is also a slice, then the mirror symmetry factorizes. And the elliptic fiber is encoded by the mirror of the 2-dimensional polytope, and the base is encoded in a simple way in terms of the structure of the base in many cases. So let me unpack this a little more. In the simplest cases, we have what I'll call a standard stacking polytope, where we basically take the polytope for P2, 3, 1, and we pile up the base over the -2, -3 point in the toric description of that. This is basically the toric encoding of a Tate-form Weierstrass model that we mentioned earlier. The mirror of that is the generic elliptic fibration over another base B tilde, where B tilde is the polytope given by taking -6 times the polar polytope of KB. And there are tens of thousands of examples of this in the KS database. So rather than saying this in complete generality, let me give you an example. Here's a picture of the toric diagram for P2. So we're going to do a 6-dimensional example. The generic elliptic fibration over the base P2 has Hodge numbers 2, 272. And so here is the base P2 encoded as a toric variety, where the rays represent the 3 different usual charts on P2. H11 of this is 1, and we can compute H21 in terms of the number of complex structure moduli, which we can read off from the dual polytope. The mirror polytope can also be thought of as an elliptic fibration over some base, and this is a picture of the toric base over which the mirror is an elliptic fibration. All of those rays represent toric divisors. This is a 2D surface, and the red rays represent -12 or -11 curves that support, in the language of these rigid divisors that I mentioned, non-Higgsable E8 gauge groups. So Dave and I at some point made a classification of all of the 2D surfaces that support elliptic Calabi-Yau threefolds. This is one of those 60,000 toric surfaces that support elliptic Calabi-Yau threefolds. The blue ones are -5 curves that support F4 factors. The green curves are -3 curves that support G2 factors, and the purple curves are G2s. The green curves are SU2s. And so we can compute, again, using Chioda-Tate-Wazier, the H11 of the base, which is the H11 of the total threefold, which is H11 of the base, which is some number we can easily compute here, 109. The rank of the gauge group, where we add up the rank of all those pieces and add 1, and we get 272. So this is a picture of the mirror symmetry of the generic elliptic fibration on P2 to the generic elliptic fibration over a much more complicated base.
Wadi,
Yeah.
I'm reminded of some little competition between Candelas et al. And some people I was working with, and I don't remember the references or even when, but that gauge group looks kind of familiar.
Yes. This is not actually that gauge group. It looks familiar because all of those big gauge groups in that.
I understand. The source of them is the same, right?
The source of them is the same. That's exactly right. The sources of them are the same. So just to fill that out, this is the mirror of the generic elliptic fibration over P2. The one with the biggest Hodge numbers is the mirror of the generic elliptic fibration over F12, which looks kind of like this picture, but the triangle is much more skewed and it's got even more junk in it.
I see.
So it's a very similar story, but a slightly more skewed triangle.
Right.
And that is another example of where mirror symmetry respects the form of the elliptic fibration. Okay, so that's for threefolds. And in this paper with Paul, we talk about much more general structures. It works if you tune Tate models. That corresponds to reduction on the dual lattice. It works for other fibers and bundle structures. There's a whole beautiful story there, which allows you, for example, to study things like the mirror of Higgsing processes and what happens to superconformal matter under a Higgs transition, which you can understand some aspects of on the mirror partner. So what I want to do today is talk about doing something like this for fourfolds, and then using that to understand the full H4XZ lattice. So I'm going to take a fourfold generalization of the P2 story that I just outlined. So now I'm going to take the base of the initial Calabi-Yau fourfold as a P3. This is now the standard stacking of that base P3 over P2, 3, 1. And now the mirror is going to be, so it's going to look very much like this picture, except instead of a triangle, we have a tetrahedron. Each tetrahedron is filled with many rays. So it's the tetrahedron whose vertices are these 4 points, like -6, -6, 18 in the three-dimensional Z3. And then there are all these rays, which give us E8, F4, G2, and SU2 factors. We've found essentially, somewhat by hand, a triangulation of the entire thing, which can be realized by triangulating a tile and then tiling it. So this here on the right is a picture of a complete triangulation of one of the 4 faces of this tetrahedron, where I've extended each of the rays so that it hits the face to make it geometrically clear what's going on. So again, these red things are E8 factors, the blue ones are F4s, the purple ones are G2s, the green ones are SU2s. Again, the G2s and SU2s come in combinations. And so this is an explicit toric threefold base which has a huge number of rays, and it's got all these non-Higgsable or rigid gauge factors. And this is going to be the mirror of the generic elliptic fibration over P3. So what I want to do now is combine the factorization of mirror symmetry with the structure I talked about at the beginning of the talk of this reduced matrix M red to get a computation of the full unimodular intersection form on H4 of XZ, which I think is something that people have not, as far as I know, in the literature computed for any actual fourfolds. But the claim is that this technology will allow us to do this. And I'm going to outline it in a very specific example, which is this P3 case, and then talk about some of the additional things you need to go further. So for P3, H11 is 2, and H31 is 3,878, and mirror symmetry exchanges H11 of the mirror Y with H31 of X. So first, let's see how to get H11 of Y. By Chiyoda-Tate Wazir, it's H11 of the base tilde, which is 2,303 from toric rays. There's a little bit of a technicality, which is those E8 factors actually have 4-6 loci singularities on them, so they have to be resolved to get a slightly non-toric base. That adds 22 to the H11. And then we have those gauge group factors. There are 34 factors of E8, so we multiply the number of E8 factors by the rank of E8 to get the total rank of the gauge group plus 1, and we get 3878, matching what we expect. So again, the goal here is to write down the full intersection form on H4 of XZ, and that will include M red of X, and it will include M red of Y, the mirror, because those things are exchanged with one another. The vertical and horizontal are exchanged under mirror symmetry. In this particular case, there is no remainder part, so it makes our life easier. Okay, so now what I want to do is talk about M red of X and M red of Y, and then the full H4 of XZ will be a unimodular lattice formed from the direct sum of those two. So again, this thing has to be unimodular or has to have a unimodular overlattice. In the P3 case, there's no gauge group. So now we can go back to this general form I wrote down for M red. It just looks like this. And there's only one base divisor. So these matrices are very simple. K is just -4, the canonical class of the base. There's only one divisor and one curve. So we get a 1 in the off diagonals. So this is all we get for M red of X. So all the rest of it has to be made up from M red of Y. So it will schematically have this form where we have the upper left 2x2 block from the base, a whole bunch of stuff from gauge factors, and then some extra surfaces that we have to understand to fill the thing out. So we expect, because this matrix -4,110 is itself unimodular, and we have a direct sum of two lattices, we expect that M red of Y is also going to be unimodular or perhaps admit a unimodular overlattice. So the upper left 2x2 block is automatically unimodular by Poincare duality, because there's a theorem that the toric curves span the Chow ring. We know that we have a nice unimodular lattice there. The E8 factors are automatically unimodular because E8 is unimodular and they live on surfaces sigma, and every surface that we get is also going to have a unimodular intersection form. So we get the tensor product of the E8 Cartan with the intersection form on those surfaces. That's already unimodular. F4 by itself is not a unimodular lattice, but there's a way of getting a unimodular lattice by an overlattice, which I will talk about in a minute. It also seems that there are some extra surfaces associated with the F4 factors. G2 cross SU2 also seems to give some extra surfaces. So I'll delve a little into the technical details here, but the idea is that we seem to be able to precisely produce this kind of unimodular structure for a pretty general class of bases. And sometimes you have to go beyond just unimodular on each side, noting that a G on one side will give either a G or a commutant of G on the other side, which ties very nicely into this sort of E8 rule that Berglund and Meyer ran into in mirror symmetry, and that Paul and I have been exploring further in various dimensional cases. So let me just go through and outline how some of this works. How do we get this H22 vert? So there are various contributions from that big matrix, remember. There are contributions from the S0 alpha, S alpha beta, and SI alpha. The S0 alpha and SI beta contribute H11 of B tilde, which is 2325, giving us 4650 for those contributions. The sum of the gauge group factors, again, this is like the calculation I did earlier for the P2 case, but just on this bigger base. We've got, again, this is the tile. These tile this enormous triangle, which is a surface of a tetrahedron. Special things happen at the vertices of the tetrahedron, where the E8 factors at the vertices of the tetrahedron only have 3 local regions that look like this corner, whereas everywhere else they have 4. So there are 30 E8 factors which live on surfaces with H11 is 22. There are 4 E8 factors that live on surfaces with H11 is 16, giving this contribution. There are 2 kinds of F4 factors. There are F4s from the corner like this, which have large H11, which is 14, and there are F4 factors that have smaller H11 here is just 2. There are various G2 factors, 2 kinds of G2 cross SU2s, the ones in the middle and the ones on the edge, which are a little bit different. Adding up all those numbers, we get some big number, 10,400. We add it all up, and the mirror symmetry tells us that we expect 15,562, and we have all but 512 of it. So we have to identify the remaining part, and we can find that as coming from extra surfaces, which are these asterisk parts of the H22 vert matrix that I mentioned, coming from things like matter surfaces, but not matter surfaces because we don't have any matter, any chiral matter associated with any of these gauge groups. So computing these in detail is a bit complicated, and we are in the process of working some of that out, but let me just outline how some of this works. For example, we have extra surfaces coming from G2 cross SU2 clusters. For instance, in the middle of this picture, we have a G2 cross SU2, and there are places where you have extra enhancements on the edges connecting those. Some of those Kodaira fibers over those curves give us extra surfaces. And so here's a general form for the matrix that will characterize those extra surfaces over the G2 cross SU2 clusters. So here we see the usual upper left 2 by 2. We see the carton of G2, the invert or the inverse killing form of G2, and then the carton of SU2. And then we have this extra surface thing here coming from these extra intersection factors. For instance, on the case of the left, we see that these guys actually are living on divisors with H11 equals 2. So they're really just locally Hirzebruch surfaces. We can compute all this, and we expect to see that the determinants of the various matrices will give us perfect squares, which is a necessary condition for an overlattice. That's a little bit complicated, and we're still actually, as of this morning, we were running into some factors of 2 and some funny issues. So I'm not going to go further into the details on that, but let me, and also I've got 3 minutes, but let me give you a little better sense of what I mean about overlattices in the F4 context. Again, writing down the H22 vert intersection form that we get from this whole complicated story I've just told you does not immediately give us a unimodular lattice, because sometimes we need to include extra vectors. That is, we need an overlattice. So here's a simple example of that. If we take the F4 inverse killing form, it looks like this. This is not a unimodular matrix. Its determinant is 4. But if we add this additional lattice vector, 0, 0, 1/2, 1/2, this has an integer inner product with everything in the lattice. It also has an integer inner product with itself, and we can actually build a overlattice of the initial lattice, which is unimodular and will give us the proper quantization for an integral lattice. The fact that H4 of XZ has to be unimodular essentially guarantees that we're going to get these kinds of extra vectors. And we are looking right now also for independent approaches that will confirm the existence of those. But there are some things using Komorov invariance and things that Menke and others have studied that will help give us other ways of confirming that. But just from the unimodularity, we know that has to be there. So we're just about there. And in fact, the first paper that hopefully will come out in not too long about this will be the example of the base P3, where both sides are unimodular. We can do an explicit calculation of what the extra stuff is and show exactly what the form of the matrix is. More generally, it's a little more complicated because there are these non-Higgsable and tuned blocks of gauge groups, which may not give us unimodular components. And then we need to glue it together with a complement, which will either have the same gauge group or the commutator, which is a structure that we've observed in all these different toric duals we've been looking at with Paul. And then furthermore, in many cases, we will have a non-trivial remainder cohomology. And then we need to have a methodology for computing the intersection form on this, which is not yet completely, something we don't yet completely have a handle on, but it's an interesting question how to complete that for those more general fourfolds. And the basic idea is this allows us to get a complete handle on H4 of XZ, which could be very useful for a lot of applications, in particular for understanding relationships between mirror symmetry, chiral matter, and things like that. I have 1 minute left, so I will conclude. We have a new general approach to understanding resolution-independent intersection forms on H22 vert, which is crucial for understanding flux compactifications in chiral matter. We have a general formula for chiral matter including for this universal GSM model. And in all the cases we've looked at, the only constraints on the sets of independent chiral matter are those that are associated with anomalies. F theory does not impose additional constraints. We have a new way of getting standard model-like constructions where 3 generations can be very natural with limited exotics, with no exotics from flux breaking of an intermediate to an SU intermediate SU5. And we can use the structure of the intersection form mred and mirror symmetry to get a computation of the full intersection form H22 in some cases, and we're aiming for all cases. And I'm out of time, and I will stop there. And thanks again for your time.
Are there questions? If you'd like to ask a question, you can raise your hand and I'll call on you. Maybe we're all so blown away. I love the beautiful diagram with the little red cluster things, but I'm going to have to study these before I have specific questions, I'm afraid. Yeah, that one, that's great. It's beautiful.
We were very happy about that picture.
Maybe you should, have an online marketing of a T-shirt with that thing on or something.
Yep. Complicated Calabi-Yau fourfolds.
Right. No. This may be the universe. I mean, it's something like that.
This may be the universe. You are here.
You are here.
Or your kitchen remodel.
Or your kitchen. Yeah, that's right. You could tile a kitchen with that.
Yeah.
It would be a little bit extreme for tiling a kitchen, I have to say. One of those tiles is great, but if you had a whole kitchen full, I think you might regret it.
Big universe, big multiverse.
Well, if there are no questions, we look forward to the papers that have some details, and let's thank Waddy again.
Okay, thanks again, everyone. Nice to see you all.
Right.
Thanks, Waddy.
Yeah, thanks a lot.